In this video, we're going to look at something called formal charge. This is one of the most fundamentally sort of useful things in organic chemistry and when studying molecules. And it's one of these lectures that we may not refer back to, but we're going to be using formal charge a lot through the rest of the semester and into Organic 2. So with that, let's get into it. Okay, so like I said, we're going to be talking about formal charge in this lecture. And the formal charge is the charge on an atom within a molecule or polyatomic ion. Okay, so molecules we've seen before. These are these collections of atoms that are bonded by covalent bonds, connected through covalent bonds. A polyatomic ion is something different. Poly means many. We're going to be looking at polymers at some point in this semester. Atomic means atoms. And then ion means something with a charge, something with an imbalance of protons and electrons. Okay, so an example of a polyatomic ion is carbonate. So, carbonate. So carbonate is CO3 minus 2. Minus 2 is in a bit of an odd place. The 3 makes sense to us. That's 3 oxygens. The minus 2, it turns out, describes something different about this collection of atoms. This says that our minus 2 charge is over is a tough word, is contained by the molecule. Maybe contained is an even worse word. Carbonate, CO3, this collection of four elements, has an overall -2 charge. The collection of CO3 has a -2 charge. Okay, so let's think about a Kekulé structure of this. Okay, so on a Kekulé structure, we would have C with 4 dots around it. And I should clarify, let's start with a Lewis dot structure. So we'll have a C with 4 dots around it, an O with 6 dots, 2 of which are separated to spread out the electrons as much as possible. And we've got a few of these O's. But in addition to this, we have 2 electrons, or 2 extra dots. Now, why is that? Why is that? Because that we have a -2 charge. And what that means is as a result of having a -2 charge here in carbonate, we're going to have 2 more electrons than I suppose we'd expect. That is to say, if we had CO3, we'd have 1 C with 4 dots, 3 O's, each of those having 6 dots around them. So we have 2 additional dots that we have to add to our Lewis dot structure. Let's start like this. Let's say we've got our C in the center. Now what I'm going to do is I'm going to attach the oxygen atoms around the outside. I really don't like to let oxygen bond to itself. That makes something called a peroxide, which is unstable. Okay, so if we look at this, we've got a Lewis dot structure and we've got extra electrons that are not bonded at these 4 positions. What we can do is if there are extra electrons bonded on neighboring atoms, we can use those extra electrons to make double bonds. So what I'm going to do is I'm just going to move this electron over here and this electron over here, and that's going to give us a double bond between these 2 atoms, between this atom and this atom. So we have a double bond. We've got a lot of dots. We still have single electrons around our remaining 2 oxygen atoms. But what we can do is we can then add, and what I'm going to do is I'm just going to clean this up. Let's calculate this. Let's calculate this. It's going to start being a little bit easier to see what's going on if we reduce the number of dots even a little. Make our lone dots bigger. Okay, so we can't take the lone dots that are left on the 2 oxygen atoms that I highlighted in the Lewis dot structure above. We can't take those and make a double bond. We really don't want to connect them to make an oxygen-oxygen single bond because that bond would be high energy and highly reactive. But instead what we can do is now we can add our 2 additional dots. Where do these 2 dots come from? Remember, I defined CO3 as having a -2 charge. So that's like me saying, okay, in this problem we have these X number of elements, H2O, draw a Lewis dot structure. I'm just adding another dimension to this by saying we have CO3 and a -2 charge, which tells you have 2 more electrons than you need. So what we can do is we can add some dots to the sort of holes in our structure, to the sites where we don't have a pair of electrons. So I've added those new electrons at those highlighted positions, and we have now 2 new lone pairs. So adding 2 electrons gives us 2 new lone pairs. Okay, now what does that mean? That means that our final Lewis dot structure is like their final Kekulé structure. It's like this, where 2 of the oxygens have 3 lone pairs. 1 of the oxygens has a double bond with 2 lone pairs. Now, what it turns out we need to do is we need to define where we added those electrons, okay? So that when somebody comes along and they look at this Lewis dot structure, they say, okay, I know where that person added their 2 additional electrons. We're going to put a -1 over the oxygen atom on the left and -1 over the oxygen atom on the right. So we add a charge for each electron that we added. So we added a charge of -1, and we positioned that over those 2 oxygen atoms. Now, with this structure, draw those dots a little bit nicer. With this structure and the negative charge, we can then see how the overall charge is -2. This collection of many atoms, this polyatomic system, many atoms, polyatomic system, has 2 -1 charged elements. And as a result, it's going to have an overall charge of -2. And so this polyatomic ion is an anion because anions have negative charges. So we had 2 additional electrons to add, and we put them on the oxygen atoms, which was nice because the oxygen atoms had 2 holes. If you want a deeper look at that, you could say the oxygen atoms are more electronegative than the carbon, so they're more likely to accept those new electrons. Okay, what we're going to do though is we're going to define the formal charge again. Now that we've seen this brief discussion, this is the charge on an individual atom in and we can have a molecule or a polyatomic ion. It's the same in either case. So the formal charge, that's that same definition from the first slide, is going to be these negative ones. It's not the -2. The -2 is the overall charge. But on those individual oxygen atoms, we have a -1 charge. What I want us to be able to do is calculate, and it's a very not too difficult, like you can do it without a calculator, but is to calculate / maybe determines a less intimidating word. The formal charge on an atom from the structure. So let's say I hand you, instead of a collection of atoms and extra electrons, instead I hand you a molecule and I say calculate the formal charge. Can we do that? I'm going to hand us back this same molecule, carbonate, CO3 -2. And I don't need to give you any additional details other than lone pairs and bonds between the elements. You need lone pairs and bonds. Without those, you can't solve this. With just the structure, or with just the collection of elements, CO3, you can't just go ahead and calculate the formal charge. What you have to do instead is propose a structure and then calculate the formal charge. But with the structure, we can determine the formal charge. The calculation is a very important equation that we should know, and that is that Fc, or formal charge, equals the group number minus the number of bonds minus the number of non-bond electrons. Group number minus the number of bonds minus the number of non-bonding electrons. Okay, what I'm going to do is I'm going to label, I have C, and then I'm going to label this O as a star, triangle, and square. So we have 3 O's, I just gave them different labels. Now let's figure out the Fc on everything. So Fc of, so the formal charge of carbon, it's going to be equal to, I guess, the group number minus the number of bonds minus the number of non-bond electrons. Okay, so for carbon, we had 4 bonds and 0 non-bonding electrons. It doesn't have any dots around the atom that aren't part of bonds. Okay, so we have -4 and -0. Now what's its group number? Its group number is 4. The group number in the periodic table. This is not its atomic number. This is the number that helps us determine the valence electron count. Okay, so 4 minus 4 minus 0 is equal to 0. What we say when we see a neutral formal charge is that we have a neutral element. Now for oxygen, we have triangle, star, and square. Okay, this was triangle, or excuse me, that was star, and then triangle looks like this, and then square looks like this without that extra pair of electrons. Okay, so oxygen in every case is group 6. It has 6 valence electrons or 6 dots around it in for the most part. Okay, so the number of bonds in both star and triangle is 1. It only has 1 bond. Notice that I keep that number as 1. I know there are 2 electrons in that bond, but bonds count for 1. In the last example, square, we have 2 bonds. Now for the number of non-bonding electrons, that's the number of dots around the outside. I think I've done this enough to where I got a little sloppy. Sorry about that. But we have 6 in the case of star and triangle, and we have 4 in the case of square. So we have 0 for the case of square, but now 6 minus 1 minus 6 is equal to -1 for the star and the triangle examples. Now, what does this mean? This means we need to label O star and O triangle with a -1 formal charge. So I handed you a blank structure that is a structure without formal charges of carbonate, and then using this formula, which you should commit this formula to long-term memory. Using this formula, you said to me, well, I need to add a -1 here and here because those have formal charges. 0 formal charges are not written. So we don't write a bunch of zeros. For the most part, the elements in our system are going to be neutral. So that's a look at formal charges in a nutshell. The equation is important, being able to take collections of polyatomic ions, that is collections of elements, which we say not only are they bonded, but the overall collection of atoms has a charge. It could be -1 or +1. In the next lecture, we'll look at an example, a quick example of how to handle this if we have polyatomic cations, that is positive formal charges, and then neutral molecules that have elements with formal charges.